Hello, in this video, I'm going to show you how to design a very simple frame system um, using Karamba 3D. I drafted a very simple frame system without any bracing in Rhino. That's just like a one-bay frame system. And I'm going to consider all the connections as fixed. Um, the first step is to transfer this geometry to Grasshopper. So I will call geometry parameter, and I will make two separate ones. Then I will right click on one of them, set multiple geometries, pick the columns, separate geometries, and then rename this parameter, and then set multiple geometries to select beams. And then I will rename this and call it beams. Then to get started with Karamba analysis, there are three main components that I should drop down from the model menu. One is create linear elements. The other one is assemble model. And then the other one is support. So I'm going to connect both columns and beams to create linear elements, and then elements to elements here. Then the next step is to define connections. So I'm going to make all the connections, both connections between beams to columns and columns to footing as rigid. So I'm going to connect points driven from the create linear element component to the support. Then in the next step, I'm going to define the load. I will drop a beam load component here. And in this example, I assume that all the beams will carry a uniformly distributed load, a kind of like gravity load with a magnitude of -4. I'm gonna give this load case a name. I will call it load case 1. And then I should define on which beams this load will act. So I will make the orientation also global, and then call list item. And I will connect elements to the list and connect the item to here. Now I should pick the right index. Since we have 4 elements here, I should call 4 index values. So I'm going to right click on the panel and click multi-line data. Now I can give the index values. I think the index values in my case are 5, 4, 6, 7. In order to see if I'm applying the load to the right beams, I'm going to connect the load to assemble model, and also drop a model view here and connect the model, assembled model to it. Now I see that all the 4 beams are selected correctly. Here, the T positions by default are 0 and 1, which are correct because we want to apply the distributed load all throughout the length of the beam. Now we're all set with assembling the model. Now it's time to run the analysis. So I'm going to analyze the model and then connect the analyzed model output to the model view. Now you can see huge deformation here. Now I can reduce the scale of visualization. And I'm going to also click on reactions to see what are the axial forces in the columns. Here we go. There we are. And then in order to see the moment diagram, the moment forces, I need to drop the beam view and connect the model to model. Here we just only have one load case. If we have multiple, we should make sure that we're picking the right load case here. Now here, I'm seeing the cross-section rendering. I will just turn it off. And I want to look into the bending moment diagram. And I'm going to choose MY. I'm going to fill the diagram and ask to include numbers. But the scale is like huge, so I will reduce the scale. And in order to see the diagram properly, not on a deformed beam, I'm going to just check off this deformation. So now I can see the diagram properly. If you think that like it's a populated diagram, you can also turn off the load here. So now we can see just the moment diagram. Now look at the absolute values of the moment diagrams. It doesn't matter if like it's negative or positive, but look at the absolute value of the given moment and find the maximum bending moment in the beams. So here is 85.33. The next step to design this beam and select the best profile, we need to use the equation for section modulus. We found the maximum bending moment here, and based on which material you're going to use to construct the frame system, you can pick the allowable bending stress. For example, for steel is 22 KSI. For different wood species might be different. So you can calculate the section modulus, make sure that you're doing the calculations correctly, because here 85.33 provided by the Karamba is in kip foot. And the allowable stress is in KSI. So you should convert foot to inch, multiply the maximum bending by 12, and then divide it by the allowable stress. So then you can find the section modulus. Then when you found the section modulus, the next step is going to our class supplemental material page under week 10 and scroll down and look at the properties of steel sections provided by AISC. And you should look into this column of section modulus SX, and probably the output of the section modulus that you calculate is not too big. It should probably be something a kind of like two-digit number. So maybe you need to scroll down into this list and pick a section whose section modulus is equal or greater than what you calculated. So if, for example, you calculated a section modulus of 40, you should look into this table, find a profile whose section modulus is equal or greater than 40. And you can actually look into the table and suggest different profiles. So there is not only one single correct answer, but you can pick multiple suitable options. And that's all about designing the beams. Then if you want to design the columns as well, you should look into the axial forces going, through the columns, which are actually the reactions. Since here we picked the connections all rigid. No bending force is transferred to the columns, so they're like just axial compression stress by the support, which is 52 kilopounds. And you know that stress equals P over A, force over the cross-sectional area. And again, you can look into the allowable stress of columns. If you look for steel, it's again 22 KSI, and the force here is 52 kilopounds. Make sure that you're considering, doing the calculation right, and find the required cross-sectional area. So then when you do the math, you can go back to this table, and this time look into profiles, cross-sectional area. So for example, here, just maximize this page, you should look into this area, this column, and find the required area, and find a profile with an area equal or greater than what you calculated. If you, for example, calculated a required area, for example, 2 square inches or 1.9 square inches, then you should probably scroll down to the bottom of the list and pick a very lightweight steel frame. And that's all.